All right, class, today we're going to qualitatively and quantitatively predict the effect of an added common ion on the pH of an aqueous solution of a weak acid or a weak base. In simpler terms, we're dealing with buffers today. So we're going to describe buffer solutions, how they're made, how they work, and we'll be able to do some calculations with them. And this lines up with the acid and base quest on buffers. So a review of the common ion effect. We've talked about the common ion effect already with KSP in the solubility product constants. Similar principle here. The extent of ionization of a weak electrolyte, here that means a weak acid, is decreased by adding to the solution a strong electrolyte that has an ion in common with the weak electrolyte. So in simpler terms, I know I've got HA, and it's going to ionize to H plus and A minus, but if it's a weak acid, the equilibrium is going to lie far to the left, as is. If I suddenly have way more A minus, that comes from my strong electrolyte, if I have way more A minus in solution, it's going to cause my equilibrium to first shift even further to the left. So if we think about it, we got to look at where can that possible strong electrolyte come from. So this leads us to a buffer. A buffer is essentially a solution of a weak conjugate acid. So here we've got HF and its conjugate base pair, which is F minus. So if we look at HF, we know HF is in weak acid. If that was to be mixed with a strong base, if we were to titrate it, we would get our salt, NaF, and H2O. Now, just like we did with our salts previously, if we have a salt, we can trace it back. We know that Na plus is going to be a spectator, it comes from a strong base, and F minus comes from our weak acid. If we're looking at a buffer, the way it gets its conjugate base pair in solution with the weak acid is by pulling from a salt. So if we mix our weak acid with a salt with the common ion, we will have our buffer. That's the simplest way to make it. So here we could take sodium fluoride and add it to a solution of HF, and now we have all of this F minus in solution, which makes sense because Na plus is a spectator, it ionizes, we've got just F minus floating around a solution in addition to HF. Okay, so to figure out how a buffer responds to changes in pH, either from a strong base or a strong acid, we need to look at both possible equilibria here. So the first one, first we know that our buffer is going to have equal amounts of HF and F minus to start. That's how we know it's at our stable pH. They're equal amounts, so we say that's probably going to be equal to 1 or roughly around there. If we add a strong base, such as sodium hydroxide, we add OH minus, we're going to decrease our HF, which makes sense. But since we're decreasing our HF, that means we're going to create more F minus. If we already have a lot of F minus in solution, and we know our Ka is very small because it's a weak acid, we're only going to make a little bit more F minus here. And overall, our pH is only going to have a minor change. It only drops a little bit. If we were to go in the opposite direction, we have still that same ratio of HF and F minus. If we add H plus and F minus together, it's going to drive the equilibrium to form more HF because we're shifting it back this way. And by shifting it back this way, we're going to get a little bit more HF and our F minus is going to decrease. But again, our K values, our Ka values are very small. Since it's very small, there's not as much of a shift that's going to happen. So we've got this buffer region where our pH is going to change, but we're not going to see huge changes in pH like you would with a strong acid or a strong base. But we can still use strong acids and strong bases to titrate these things, and when we do, it's going to take quite a bit to get this thing going. When we're looking at a buffer region on a graph, you'll see this kind of big, broad, flat line here. And this area, this is a buffer region where the pH really doesn't change much. And it's due to this common ion effect. So there's a way we can calculate this. It's called the Henderson Hasselbalch equation. The form that's probably going to be on your formula sheet is going to look like this. It'll be, not like that, sorry. It's going to look like this. pH is equal to the pKa plus log of the base concentration over the acid concentration. Again, that's the conjugate base, conjugate acid. They like to write it A minus and HA. That's the other version you might see. So HA and A minus. Now, I want to steer away from using this. You certainly can if you would like, but this version of the equation is a little bit trickier to manage. We're going to use this chunk right here. If we took the log of this entire thing, we would end up getting this, which is what's on your formula sheet, but it kind of overcomplicates things. So we're going to use this version here, where, again, this is our weak acid and weak base. And when we're talking about that, these are conjugates of each other, right? So keep that in mind. All right, our first calculation. Calculate the pH of 0.5 liters of a buffer solution composed of 0.50 molar formic acid and 0.70 sodium formate before and after adding 10 milliliters of 1 molar hydrochloric acid. And they give us our Ka. Holy wow, this sounds confusing because there are so many numbers. It's really not that bad. So first, let's calculate the pH before. Sodium formate, if you see an 8, that they're talking about our A minus there. So we really can put this in terms of HA. Here's our HA concentration. Here's our A minus concentration, right? So if we're looking at before, we know that for the before reaction, we have H plus equals the Ka times the concentration of our weak acid, so yeah, weak acid, sorry. Concentration of my weak acid over my concentration of my weak base, okay? And if I plug my numbers in, that means I've got 1.8 times 10 to the negative fourth is my Ka, times 0.50 molar over 0.70 molar. It's weak acid, weak base. All right. A minus is a weak base, right? So this is my weak base. I'm going to change this to a W, weak acid. That way we can keep track, right? Keep it consistent. All right. So I'll go to my calculator, and I've got 0.5 divided by 0.7 times 1.8 e to the negative fourth, and I get my H plus concentration of 1.29 times 10 to the negative fourth, and of course I'm going to do negative log of that. So 1.29 times 10 to the negative fourth. So, not eraser. H plus equals 1.29 10 to the negative fourth. Therefore, pH is going to equal 3.8 8, 9. Okay, so I know I'm dealing with a weak acid here because my pH is in the 3 to 4 range, and or 3 to 5 range rather, and that makes sense. If it was a strong acid, then I'd have a much lower pH. Alright, so now we've got the before part done. We want to look at after. So after adding 10 milliliters, here's what I'm going to want to do here. I want to put everything in moles. I need to know the moles of my acid. So we're looking at the after end. My moles of acid. So 10 ml of 1 molar HCl. That's going to give me 1.0 molar times 0.01 liter, which means 0.01 moles of acid are being added. Alright, I also need to know my moles of weak acid. So I said it was 0.5 liters of each of these, right? So 0.5 liters times 0.50 means 0.25 moles of my weak acid, and 0.5 liters times 0.70 molar, which is 0.35 moles of my weak base. Okay, now that I have everything in moles, I want to figure out my change. Whenever we do our change, we're going to do our change in moles. Okay, so I have my weak acid. Again, same as before, weak acid over weak base, but I need to look at my change. So I have 0.25 moles, and I've got 0.35 moles. The hardest part is figuring out whether I'm going to add on top or subtract on top, and vice versa with the bottom. One side is always adding, one side is always being subtracted. So if we think about this, we're adding HCl, we're adding H+, we're adding H+, it's going to be, we're going to become more acidic, and therefore that means we're going to be adding to our acid side. So since we're becoming more acidic here we are losing. Alright, so we're becoming more acidic, therefore we're adding to the weak acid, and we're becoming less basic, so therefore we're taking away from our weak base. Okay, so always think about it conceptually, trying to figure out the pluses and minuses. So here we get 0.26 mole over 0.34 mole, and now I have my ratio. And I need to multiply this by my Ka, 1.8 times 10 to the negative 4th. Okay, so 0.26 divided by 0.34 times 1.8 e to the negative 4th. And I get 1.376, so 1.38 times 10 to the negative 4th. So this is 1.38 10 to the negative 4th molar for my H plus concentration. Negative log of my H plus is going to equal my pH. Alright, so negative log, and I get 3.86. Alright, so my pH after is 3.86. So even though we added 10 milliliters of a 1 molar strong acid to this pretty weak acid solution, since there is plenty of A- in excess there, plenty of our weak base, it allows us to resist our change in pH. Even though our weak acid concentration goes up a little bit, our weak base concentration compensates, and we have a tiny drop in pH. Okay, let's do another. So this one says, using an acetic acid sodium acetate buffer solution, what ratio of acid to conjugate base will you need to maintain your pH at 5.0? All right. So this one is rather conceptual. They want to know the ratio, and the ratio is pretty easy. If they're looking at ratio, we're looking at our equation. We know that H plus is equal to the Ka times the weak acid over the weak base, right? This is our ratio. This is what we're looking for here. So they tell us we want to maintain at a pH of 5. A pH equal to 5 means that H plus equals 1.0 times 10 to the negative fifth. Alright, so I know that I could rearrange my weak acid over my weak base ratio is going to be my H plus 1.0 times 10 to the negative fifth divided by my Ka 1.8 times 10 to the negative fifth. Look at that. Those cancel out. We get a ratio of 1 to 1.8 for my weak acid to my weak base. Alright. Pretty simple. Alright. Okay, so number 3, it says a buffered solution contains 0.25 molar NH3, that's a base, right? And ammonium chloride, so that's our acid here. Cl is just a spectator, and ammonium, we're looking at ammonium and ammonia, right? So this is our base. Alright, so I want to know my pH of my solution. So this is my before, H plus, I've got my Ka times my weak acid over my weak base. Alright, sorry, I should be more careful with my brackets here. Weak acid, weak base. Okay. So what that means is that I need my Ka. Oh, but what did they give me? They gave me Kb. So we got to convert. We know that Kw over Kb gives me my Ka. So I've got 1.0 times 10 to the negative 14th and 1.8 times 10 to the negative 5th. And I'm going to multiply that by my concentration of 0.40 molar, that's my acid here, and 0.25 molar, that's my base. Alright, and when I do that, so 1 e to the negative 14th divided by 1.8 to the negative 5th, 5.56 times 10 to the negative 5th is going to be my my Kb value. Sorry, 10 to the negative 10th. My bad. 5.56 times 10 to the negative 10th is my Kb times 0.4 divided by 0.25. All right, and I get 8.9. 8.9 times 10 to the negative 10th. If I do my pH of that, negative log 9.05, which makes sense, right? Because ammonia is a base. So I'm looking at a basic buffer solution here. Okay. All right, now I want to know the pH when 0.10 moles of HCl is added to 1 liter of the buffered solution. Well, they've made it easy for us. We're looking at 1 liter of solution. So 1 liter, therefore that means we've got 0.40 moles of my NH4Cl and 0.25 moles of NH3, and then we don't need to do anything else. Remember, it's easier to do the buffer problems when everything's in moles. Volume just messes us up, okay? So convert everything to moles first. And 0.10 moles of HCl. Okay. So let's look. We've got my Kb. So H plus, not my Kb, my Ka. H plus equals my Ka. So 5.5, 5 times 10 to the negative 10th. That's what I calculated in the previous problem. And I've got 0.40 moles and 0.25 moles Alright, and I gotta figure out my direction this time. Again, what am I doing? I am adding what? I am adding acid, therefore I'm becoming more acidic. So I'm adding 0.10 to the top, and I'm subtracting 0.1 from the bottom. Okay? So this means I've got 0.5 and 0.15, right? So this is 0.5 over 0.15 times 5.5 times 10 to the negative 10th. I'm going to get a value of, so 5.55 e negative 10 times 0.5 divided by 0.15, 1.85 times 10 to the negative 9th. Is that what that, yeah. So I get 1.85 times 10 to the negative 9th molar H plus. pH is going to be equal to the negative log of that. And let's see how much it resisted. 8.73. Okay, so that's a considerable drop. But still, it went from basically 9.0 or 9.1 to 8.7. That's still pretty substantial. That resisted a fair amount. Okay. All right. Chemist needs a solution buffered at a pH of 4.30 and can choose from the following list of acids and their soluble salt. Calculate the ratio of acid and base required for each system to yield a pH of 4.30, and we want to know which one works best. Okay. Well, here's the deal. If you look at each of these Ka values, the one where the ratio is closest to 1 is going to be the best one for maintaining our pH, right? As we talked about before, if our ratio of our A minus, or our salt, the ratio of our salt ion to our weak acid ion is closest to 1, then our Ka times 1 is going to be equal to our H plus concentration, right? If we think about our equation, Ka times weak acid over weak base. If this is 1 times my Ka equals H plus. For a solution to be buffered at a pH of 4.30, we want something with a Ka that's really close to my pH of 4.3, right? So when I approach this, I want to figure out which pKa is closest to my pH, because that will be the one that resists change the most. So I could go through and calculate all of these. I could do negative log basically of everything, and that would be the easy way out. If I do negative log of each of these, I'd be able to figure out which pK is closest to 4.3. The other way I could do this is looking at the ratio of my H plus over my Ka, and that's going to be equal to my weak acid and weak base ratio. And the one that is closest to 1 will also be the best. So there's two ways you can do that. So go ahead, try it. Which one do you come up with? Should have come up with benzoic acid. If we do 10 to the negative 4.30, so 10 to the negative pH, that gives us the H plus concentration we're looking for. So 10 to the negative 4.3, 5.01, so basically 5.0 times 10 to the negative fifth is my H plus. All right. So I want to figure out which of those H plus or which of those Ka values is closest to my H plus. The one that is closest is benzoic acid. Hypochlorous acid is way too small. Chloroacetic acid is way too big. The only two real contenders here are these. 6.4 is closer to 5 than 1.3 is. So a couple ways you could do it. If you did all the math, you could do it that way. If you just reasoned and looked at by comparison which is closest, benzoic acid should have been your safe bet. Okay, that is all for today.